What if I told you that in the world of AI, bigger isn't always better? Welcome to Summarize Science, where today we're looking at a fascinating case where a larger, more complex AI model was actually outperformed by its smaller sibling. Researchers were puzzled by this because it goes against the common assumption that more power equals better results. They studied how these vision transformers, which are AIs that understand images, process information layer by layer. They discovered a consistent three-stage pattern they call Cliff-Plateau-Climb. Think of it like this. The cliff is where the AI first breaks down an image into pieces and gives each piece a unique identity. The plateau is a long working phase where it analyzes these pieces individually. Finally, the climb is where it brings all the information back together to make a final decision, like identifying a cat in a photo. The researchers looked at three models: small, base, medium, and large. While all three followed this pattern, the key difference was in the plateau phase, which got longer as models got deeper. But surprisingly, the medium-sized base model ended up with the most organized and effective final representation, as shown by the metrics here. To figure out why, they developed a new tool called the Information Scrambling Index. This measures how much information is being mixed between the different parts of the image as the AI works. They found that the small model suffered from communication collapse; its parts didn't talk to each other enough. The large model had the opposite problem: chaotic diffusion. Its extra layers just kept overmixing the information, like a meeting with too many people talking at once, leading to inefficiency. The medium model, however, achieved a controlled consensus, a perfect Goldilocks amount of communication. One of the most surprising discoveries was about a special part of the AI called the CLS token. It was designed to be a central manager, collecting all the information to make the final call. But the best-performing model actually learned to bypass this manager. It found it was more efficient to create a distributed consensus, where the image patches worked things out amongst themselves. The larger model struggled with this, showing instability in its central hub right when it needed to be stable. So, let's recap the key points. The study shows that simply adding more layers to an AI can be counterproductive if it leads to chaotic information mixing. The most successful model was the one with just enough depth to have controlled, efficient communication, and it even learned to work around its own designed-in bottleneck. What does this mean for the future? It suggests we can build smarter, more efficient AI by focusing on computational strategy, not just brute force size. Tools like the Scrambling Index could act as early warnings, helping designers create models that learn effectively without wasting massive amounts of energy and computing power.